In this presentation, I will discuss the second proof of the particle nature of electromagnetic radiation and the wave behavior of electrons. The second proof that electromagnetic radiation can at times act as a particle can be observed when high-frequency electromagnetic radiation collides with an electron. This experiment is called the Compton effect. In this experiment, X-rays collided with an electron, causing a change in speed and direction of the electron and a change in frequency and direction of the X-ray. According to wave theory, if the X-rays were acting like a wave, there would be no change in the X-ray's frequency. The energy and momentum lost by the X-ray photon was exactly equal to the energy and momentum gained by the electron. When the X-rays collided with the electrons, their direction changed and wavelength increased. Since the wavelength increases, we know that the frequency decreases. One of the most puzzling characteristics of quantum theory is, even while we are talking about X-rays acting like particles, we still use wave terms like frequency. Many scientists reconcile this contradiction by explaining that electromagnetic waves act like waves while they travel through space and act like particles when they interact energetically with extremely small particles. Momentum and energy was conserved in this interaction. The photon's energy and momentum decrease equals the electron's energy and momentum increase. One of the reasons why humans try to limit their exposure to a high-energy electromagnetic radiation like X-rays and gamma radiation is that these radiations have the ability to destroy cells by dislodging the electrons in the atoms that make up DNA. We can see from the equation that the momentum of a photon is inversely proportional to the wavelength of the electromagnetic radiation. Therefore, the closer you get to the left side of the chart in front of you, the more damage the ray can do when it enters the body. Since violet is the color with the highest frequency, it has the greatest momentum. In summary, when electromagnetic radiations with a high frequency and a low wavelength, like X-rays, collide with an electron, they are able to change the speed and direction of these electrons. The photon electron's mass, energy, and momentum is always conserved. One of the surprising observations in this experiment was that the X-rays had a smaller frequency and a larger wavelength after the collision. The decrease in frequency and increase in wavelength was due to a loss in energy that was exactly equal to the energy gained by the electron. Part 2, Matter Waves. Just when you thought modern physics couldn't get any weirder, a young physicist named Louis de Broglie proposed in his doctoral thesis that if a particle of mass were extremely small, it would move through space like a wave. His theory predicted that a beam of electrons would produce an interference pattern if it passed through a double slit, just like light. A beam of electrons would spread out when it passed through a small opening and interfere with itself both constructively and destructively. 3 years after de Broglie made this assertion, two scientists at Bell Labs fired slow-moving electrons through the small gaps in a crystalline nickel target and observed the beam spread out and produce a diffraction pattern. Later on, scientists passed a beam of electrons through a set of double slits and created an interference pattern like the kind produced by light waves. Our current understanding of the electron is that its mass and charge spread out like a wave, and the moment it interacts with the external world, the wave function collapses and it lands in a single place, like a particle. The places in this animation where you see no electrons represent a destructive overlap of the electron's waves. So why was it that only tiny objects like electrons, atoms, and molecules move through space like a wave? De Broglie's equation predicted that the wavelength or wave behavior of any form of matter was inversely proportional to the object's momentum. So if the object's momentum was very low, its wavelength was high, and its wave behavior was more noticeable. De Broglie's equation showed that ordinary objects like a small grain of sand had a mass and momentum that was far too large for it to ever show a noticeable wave behavior. In fact, even microscopic objects would have an insignificant wave behavior when they moved. So is light a wave or a particle? Can particles diffract and interfere like waves? The answer is that waves and very small objects have a dual nature. Light in all electromagnetic radiation behaves like a wave when it travels through space and interacts with other waves, and like a particle when it interacts with very small objects. Very tiny objects move through space and interact as a wave, but collapse into a particle when they interact with other matter. This is the end of my presentation on the Compton effect and matter waves.